Welcome back to day 2 of the Cyberbot Educator Workshop. This is the 2025 installation on March 5th. Here again is the slideshow, which has all the links that I will be pasting into you. And let's see. I need to get the chat up. There it is, and here you go. Do bookmark that one, or keep the link in your notes so that you can get back to the slideshow and potentially follow any links that I followed during the workshop. All right. As with before, if you have a single screen, it's probably best to exit the full screen view that Zoom puts you in when I am in presenter mode. So you can click view, basically move your mouse around in front of the presentation, click view, select exit full screen, and then tile your windows so that the presentation is side by side with a Chrome or Edge browser that has the microbit Python editor. That's python.microbit.org, open and ready to write scripts. So today we will be talking about Python scripts for navigation, talk a little bit about circuits. We'll talk about sounds if time permits, and then go into our first sensor-based navigation, which is with touch sensors. And then for your assignment, you'll be building the infrared sensors to experiment with on Friday. And also for the assignment, there will be, of course, making sure you can log into learn.parallax.com. We'll talk about that right at the end. Okay, so starting off with navigation, or maybe I should back up a little bit. So the assignment was to essentially take all these parts right here and then follow the instructions here, and then once you're done, you'll have a Cyberbot robot that looks like this, except for without the circuits built on the breadboard. So we should all have our Cyberbot robots looking something like this. And bear with me while I get some windows off screen organized here. Okay, almost ready. Sorry about the delay or the interruption. Uh-oh. Okay. So here we have my Cyberbot robot. And then it's good to have a little tray handy during the 5-minute break. If you didn't get one, you know, something like a small paper bowl would be nice to store all the small circuit parts in for building the whiskers. And so yes, so we are starting with the Cyberbot robot without circuits, and we'll talk first about navigation. We looked at how these bot of, and then the IO pin the servo is connected to. So that is shown right up here. So if you'll recall, it was bought with 18 in parentheses. And I don't know if this is visible or not, but here we have P18, and that's what our left servo should be connected to. And then P19 is what our right servo should be connected to. And because of those connections, that is why in our script we will say bot of 18 or bot of 19, and that is what selects the IO pin to send a servo control signal to. And then dot servo underscore speed will set the speed. And the speed ranges from 0, which is stop, and you can also use none for stop. And the stop band is roughly in the -15 to 15 range, although you may find that yours is a little bit narrower, more in the ±3 range. But nominally in name only, we expect it to be in the ±15 range. That in here, I think it's the best way to say it is that we're not going to guarantee that the robot wheel is going to move, but then once you're outside the -15 to 15 range, we can be pretty sure that the wheel will move, and then all the way up to -115. And so this would be the slowest possible clockwise, and then -115 is as fast as it can possibly go. You can use larger numbers, and we call that overdrive because basically you're asking the servo for more speed than it can give you. The same applies with positive values, except for the negative values were clockwise, and then the positive values make the wheel turn counterclockwise. And so we call this number the velocity argument, and then this number the pin argument. So bot of pin, that's the pin in parentheses, dot servo underscore speed of velocity. And so remember, there's a sign that you can use, the negative sign for clockwise, and then the absence of a negative sign meaning a positive value for counterclockwise. Let's take a look at the front, back, left, and right of the robot. And the reason it's standing on its nose right now is because the activity that we're going to start, we're just going to repeat some of our tests. And the first one will be to make sure that the left wheel turns when the P18 or the 18 argument is used here, and then that the right wheel turns when this argument is 19. And so that will be our first test, which we'll do momentarily. I'm not surprised. We get quite a number of students who don't remember their counterclockwise and clockwise. I think that's partially due to the advent of digital clocks and digital timekeeping. And so this right here is a program that I'd like you to try, but I'm actually going to have you try a slightly different variation of it. So bear with me. I'm going to paste this into my editor and modify it just a bit. And what I want to do with this script is just make sure that the left wheel turns. That's this one, when the P18 argument is used, and the right wheel turns when the P19 or when the 19 argument is used. So bear with me a second while I modify this script. So what I'm doing is I'm deleting all the 19 servo control. And so we'll try this. I'm going to use 30 to keep the speed low enough, hopefully, to be visible on the Zoom presentation. In fact, I'll reduce it to 25, and that will turn for 3 seconds. I'm going to make it turn for 10 seconds just so there's time to talk about it. Okay, so let's see if this works. I'm going to set my robot on its nose. And then what we are expecting here is the left wheel to turn when I run the script. Let's see if I made a mistake with okay, so the left wheel is turning. So this one is turning. And incidentally, to get this to work, you will have to set your power switch all the way over to the right. That's going to be position 2. So this right here is position 0. And then if you move it 1 slot forward, it will turn the one light on. So that's power to everything except for the servos. And then this is power to everything, including the servos. Now, if you want to restart this program or this script, there's a reset button underneath the microbit. It's right here. And you can press and release that, and then the wheel will start turning again. So with that said, I would like, oh, and then one last thing. If you discover that this wheel, the right wheel, turns when the left wheel is supposed to turn, that's going to mean that these servo cables are swapped. Also, I would like you to double check and make sure that your cables that have the white wires closest to the edge of the board, and then the black wires would be closer to this side of the board. Okay, so let's paste this over. Now you will need to open a copy of your Cyberbot template script. So the template that you downloaded and saved the previous workshop session, you'll want to open that. And then Control A, Control V is one way to do it, or you can essentially shade the whole thing and then right click and paste over it. I pasted as plain text, but it doesn't matter. Okay, so with all that said, here now is the script that I want you to try. And then go ahead and give me a thumbs up once you have verified that your left wheel turns. Okay, 3 thumbs up. Very good. So we got a few more people, I think, who are still working on it. Four thumbs up. Good job. 5. All right. Things are really looking up now. 6. Wonderful. 7. Marvelous. Okay, well, just give me a shout out if you need more time. I think everybody's okay here. So now, the next thing I'd like to do is have all of you modify this script so that it is sending its servo control signals to P19. That's the servo that the that's connected to the cable that goes to the left, to the right servo. And when you run that modified script, now we're going to expect this wheel right here to turn, the right wheel. And once you've got that in place, give me another thumbs up and we will move on. So this is a test, incidentally, that is in the that's in the tutorials, or pardon me, in the lessons. Very good. 2 thumbs up. 3, 4, 5, 6. Oh, you guys are doing great. 7, 8. Excellent. Okay. Let me show you what that looks like in the lesson. It's kind of hard to see, but there's when you click the image, there's usually a link attached to it. It's appearing a little bit below my taskbar. See if I maximize this. So now it's filling. Okay, so here we go. So now if I click the image, you can see the link. And now the link is mostly obscured, but if I click it, it will still take us to the wheel speed control lesson. And this is the place where students normally, if they have pre-factory centered servos, this is normally where they first run into testing the wheel speeds. And so the lesson instructions take them through gathering their parts, through making sure to connect their battery supply, their USB programming cable, and setting the switch to 0 in this case. The microbit can still accept scripts because it's getting its power from the USB cable. Once you have the USB cable disconnected, the entire system's off. But when the USB cable is connected, you can always load scripts into the microbit. And then this is where that robot orientation picture comes from. And the clockwise and counterclockwise reminder. And then here's the script that the students enter. I'm trying to get them to put their hands on the keyboard and type this script. And then we have the setting the power switch to 2. And then they talk about how it works. And then the students are challenged to experiment with the pin and also with the servo speed. And we actually give them a set of suggested speeds to put into the bot of 18 servo speed. And then they fill out a table where they discover that, incidentally, this speed is maintained for 6 seconds. So students can count, they can put a little, piece of masking tape on the wheel, for example, and they can count how many times that goes around and then multiply by 10 to get their revolutions per minute, or RPM. And that's a nice way to measure the wheel speed. And once they've measured the wheel speed, they enter it into the little worksheet here, and they'll find out that negative 200 is about as fast as negative 115, because everything above negative, or below, I should say, negative 115 all the way to negative 200 is going to be overdrive. And likewise with 115 to 200, that also should be about the same because it's overdrive. And then they'll also notice kind of a linear progression. So with 20, it'll be going kind of slow, 40 faster, 65 faster still, 90 faster, and then 115 is top speed. And we talk about a transfer function graph. So here is that stop band where nothing happens when you give it really slow speeds in the plus and minus 15 range. And this also talks about that the servo speeds, if you give it identical, if you pick identical speeds, they won't necessarily map to identical velocity arguments. There's usually a little bit of a discrepancy between the left and the right servo, which has to be corrected in order to get it to go straight forward. And this also explains how the statements, the baud of 18, servo speed of statements relate to the high-low signals. If you connect a light to the white line that goes to the servo, you would actually, well, you'd have to use a high-speed camera, but if you did, you would be able to see the light flickering. It flickers at 50 times per second. 27 times per second is pretty much the human persistence of vision, where if something's flickering faster than that, it just looks like a solid light. And so at 50 times a second, it's impossible to see. Aside from that, the amount of time the light is on, it's a short time here, but it's even a shorter time here, and so it'll appear dimmer, and it's a longer time here, so it'll appear a little bit less dim. And servo speed of 0, what that does is sends 1 1/2 millisecond on signals. Again, these are signals that would turn on a light, an LED light, if it was attached to the control line. And by applying 3.3 volts, and then it applies 0 volts for most of the time, and then another 1 1/2 millisecond, 20 milliseconds later. And it does that over and over again, 50 times a second. So that is 0. If we go down to negative 200, that's actually subtracting 0.2 milliseconds from the high time. So it's actually the number of millionths of seconds that we're subtracting from, or that we're reducing from that 1.5 millisecond. And then up here, if we use servo speed of positive 200, we're adding 200 microseconds, as in 200 millionths of a second, or 0.2 milliseconds, to get from the stop speed of 1.5 milliseconds to the max overdrive of 1.7 milliseconds. So that is what the signals look like that go to the servos. And they're begotten from radio-controlled hobby servos, which behave similarly, and they used radio waves in bursts that would last a certain amount of time, and then that would be changed into this kind of signal on the remote controlled airplane or boat or car. A little bit of background information for you there. And let's see here. So we've made sure that we've got both wheels turning roughly the same speed. And I think we're probably okay with just knowing that the larger the number, ooh, it looks like I have a few missing negative signs there. Sorry about that. That the larger the magnitude of the number, be it positive or negative, the higher the speed. Okay, next up, making the robot go forward and backward. And I'm just going to go back to the previous page to show you that it's the immediate next page. So we are here in wheel speed control. Are the servos centered? Basically, since the answer is yes, you can just skip forward to here, because again, these are factory centered servos. They know what their 0 speed signal is supposed to be. And let's see, So then the next page after wheel speed control is immediately below it in the contents. And you can also, after having gone through all that, hit the next page button. So here we are at forward, backward, and straightening curves. So forward is a little bit of a brain teaser for some students, because the way it works is that if you're looking at the right side of the robot, for what I like to ask students, okay, what direction does the wheel have to turn? And I will actually sort of walk in a direction with my right arm rotating as though it's a wheel propelling me forward, to show them that to try to emphasize this idea that it has to turn clockwise. And then I'll walk the other direction with my right arm kind of, in a swimming motion, going counterclockwise. And so do keep in mind that these wheels, in order to have the robot go forward, the wheels have to be turning in opposite directions. And that also applies to going backwards. And for turning in place to the left or right, the wheel speeds can be identical. And we'll get to that in the turns chapter. So I revisit this wheel speed a lot because I think students will benefit from having it to refer to on several pages. And then we add in here an example of, okay, to make it go about half of full speed forward, we can give the left wheel baud of 18 servo speed 65, and the right wheel baud of 19 servo speed of -65. I hope I said positive 65 up here. If I didn't, I meant plain old 65 for the left servo connected to P18, and a speed of -65 for the right servo connected to P19. So let's try this script, which I need to find for you. I believe that this is it. Okay, here we go. So with this one, it's okay now to put the wheels on the ground. And by the way, what you might notice is that it curves instead of going straight ahead, which we will talk about next. Okay, and for the demonstration on camera, I think I'll reduce the speed to plus and minus 30 so that it just creeps along. Send to microbit. Now remember, there's that little reset button underneath the microbit next to the USB cable, so you can restart this program after it runs out of statements, because it only goes for 3 seconds and then stops. And so you can either hit send to microbit again or hit that reset button. Only when you're unplugged from USB would you be able to turn the power switch, the 3-position power switch, off and back on to make that work. Okay, so restart. My robot isn't really curving very much. That's not a bad thing, except for that I was hoping to really demonstrate. Okay, it's curving a little to the left. think we could work with that. Success, everyone. Please signify by showing me some thumbs up. 1, 2, 3. Okay, good, good. 4, 5. 6. Okay, well, give me a shout out if you need if you need some extra time. 7, looking good. Excellent. Give me a shout out if you need some extra time. What I want to talk about is this idea of the robot curving a little bit. So this can be corrected in software is the way embedded system speaks refers to it. And the way that works is, let's say that your robot is curving to the right when it has that half-speed forward signal. Well, that means that the left wheel is going faster than the right wheel. So the best way to do it is to slow down the left wheel, because that's always an option, or slow down the faster wheel, because that's always an option, even at top speed. At half speed, sure, we can speed up the slower wheel, but what happens when you get to top speed? You can't speed up the slower wheel anymore. So that's why I always recommend slowing down the faster wheel. Let's see here. Want to just verify what my robot is doing here. I think it was turning a little to the left. It looks so, that looked perfectly straight. No, it's turning a little to the left, but it's so little that I really think, like, maybe if I just shave 2 off the right wheel, so -28 instead of -30, and send a microbit. Looks like I lost focus here. It's actually still curving a little bit to the left. And so let's try -25. Well, that's definitely curving to the right now. So maybe I'll go back to that 28. And that's essentially what you will be guiding your students through. And having them record what turns out to be the wheel speeds that gets their robot to go straight forward. And once they've got that, they can build on it. For example, it's not really great to have the robot curving when you want it to draw a rectangle or a square on the ground, for example. Okay, so no need to worry about having everything go perfectly straightforward. Next up, let's talk about actually, let me make sure that I've got everything covered on this page of the lesson. Okay, so we talked about direction, counterclockwise and clockwise, how the servo speeds relate, how we have to use a negative value on the right wheel to go forward. And then, of course, it would, all of these things would be in reverse. So that's the next thing I would like you all to try, is let's have it back up. Let's try making it back up, and don't worry about correcting the, if it's drawing an arc, just, that's fine for now. We don't need to worry about that. But we do want to make sure that our robot dutifully backs up when we switch the arguments or switch the signs of the arguments. So if I say -30 in the first statement and +30 in the second, and then run that, there we go with reverse. Okay, and then here we have the part where the in the lesson where the students get to straighten out their own robots' paths and then travel in reverse. And a few extra worksheet type challenges right there. Okay, so next up is left and right turns. So to turn left, the left wheel needs to be turning clockwise and the right wheel needs to be turning, I'm sorry, the left, yeah, that's right. The left wheel needs to be turning clockwise and the right wheel needs to be turning clockwise. And then to turn in place to the right, the left wheel needs to be turning counterclockwise, as does the right wheel. And so you can challenge the students of what to fill in there. And so if we want to make a left and a right turn, what I did is I included some example script, and it's part of a larger script. So here is the example of turning left in place using -75 in both velocity arguments, and then +75 in both velocity arguments to turn right. And that's part of a larger program that goes forward, turns left in place, turns right in place, and then backs up. And it doesn't necessarily back up to the same exact place it started from, because there's some speed up, slow down errors, and a number of other errors. And so students will find themselves wanting to tune this in some cases to get to exactly where the robot started. So let me paste this one into you. There you go. And I think I'm gonna slow everything down here for the camera. Make it perform the maneuver for twice as long also. Another thing I find that students get confused about is that not all students, let's just say some students in a given group will have a little bit of trouble with the idea that if you increase the time, it increases the distance traveled or the angle turned. And so it will often take some reinforcement of how that works. Students often answer, well, what if you want it to go farther? Oh, I increased the speed. Well, what if you've got max speed and you still want it to go farther? I'm not sure. Well, you increase the time. And so this is the turning in place example, where it goes forward, then rotates left, then rotates right, then backs up. And as you can see, it didn't quite reach where it started. And again, that's the kind of thing that takes tuning. However, we do have a upgrade servo that has built-in position awareness, and will be demonstrating that on day 3. Okay, how are we doing? Has everybody got that example going? 1 thumb up, 2 thumbs up. Very good. 3, 4 thumbs up. 5. Great work, everyone. All right, well, again, just unmute yourself and give me a shout out, or say something in the chat if you need more time. There are other types of turns introduced on the turns page. So we're starting with the in place turn, but there is also the pivot turn, which is pretty easy. Simply go forward with one wheel and then keep the other wheel still. You could actually pivot backward too. So you could go backward with a wheel and keep the other wheel still as well. And so here are some pivot turns examples for you. There you go. Those sleep times are pretty long, actually. I hope your robot doesn't get too tangled up in its cable. I'm slowing mine way down again so that we can just see this on the document camera. I think I might have forgotten to slow down one of those wheel speeds. 25. Oh, that's weird. Really seem to go fast there. Oh, and this time I didn't have the switch set to position 2. So I just I'm going to need to examine that. I do not understand why. Oh, there's the one I missed. Okay, let's try again. So there's the pivot to the left forward, the pivot to the right forward, pivot to the left backward, and pivot to the right backward. Well, since we were eliminating curves, we probably know about curves already. All you have to do is make one wheel travel slower than the other to make the robot travel in an arc. And here is some nice arc code for you. I'm going to change the negative signs on the second one just to get, no, that's not what I want to do. I'm going to swap the values so that, let's leave it as is. Basically, it's going to do a wider arc and then a narrower arc. I will put in a stop between the two arcs to highlight that. So that's the wide arc, and then that's a slightly narrower arc. Let's see how far I can bring down that second value. Let's try 15. There we go. I'll run that one again. This is a place where we really start to see how coding principles can map to navigation. It gives a more tangible sense of what the script can do. The result is tangible as opposed to something you might see on the screen, just reporting values, for example, in a terminal can only really go so far. Doesn't really retain student interest in my experience. Whereas this, I think, keeps them engaged a little more and also drives the point home. You'll see in a second what I'm talking about. I'd better jump forward actually, since I up and said that. The reason for that is that this script right here has statements that make the robot travel forward for 3 seconds and then turn in place for 6/10 of a second and then stop. And the question is, okay, well, now that we have this maneuver, how about if you make the robot draw a square? And how about if you use some of the tricks we talked about in the earlier chapter of writing microbit programs, namely the for loop? And so instead of copying these 6 statements and then pasting them 3 more times below these 2 routines, students can instead add the for n in range 0 to 4 to make it repeat 4 times, and then indent those two maneuvers so that they are part of the for loop. And then this will be n is 1, this will be n is 2, n is 3, and n is 4. I'm sorry, this will be n is 0, n is 1, n is 2, and n is 3. And then because of the way for loops work in Python, it bails out before it gets to 4. And then we end up executing these two statements down here, the none statements, to stop the wheels from turning. So I would like you to try this next. Feel free to reduce your wheel speed so you can do it on your table as I am. Or you can unplug your bot, put it on the floor, and then plug it back in if you go at full speed. Actually, I apologize. I should have had you try the forward and turn right first. And what students have to do here is they have to tune their forward and turn right so it goes forward straight and then makes a 90-degree turn. And this is again where we need to emphasize the idea that the amount of time can affect the turn just as much as the speed can. So let's see how that works. Slowing my speeds way down. Okay, so I'm curving to the left and then turned to the right. So there's a little bit of adjusting that I need to do. Probably at your higher speeds, the servo curves will be less pronounced. Let's see. I want to see that again. Okay, so it's curving to the left, and then it didn't, and it only turned about 45 degrees, so I need to double the time it turns. A little more than double, I'd say. Okay, so we want to slow down the right wheel. And then we want to slightly more than double the turn time, although the curving may have contributed to it. So let's just double the turn time. Oh, that looks nice and straight, but not enough turn. And so this is, again, an example of what the students will do in class. Wow. Almost. I wonder how much the cable is preventing it from turning here. I'm gonna set it on the other side and see how we do. Okay, that's actually a perfect turn. So now I know my magic numbers here. And then I can come back and grab the draw a square script from the chat. It was the one immediately before forward, right, and stop. Okay, so -22 and 1750. 25, -22, $17.50. Send to microbit. Oh, I'm actually going to turn off the power. It's going to go a little bit too far with this 3,000 distance. Let's try 2,000 for 2 seconds of travel. Oh, I loaded it, but didn't turn the power on. There we go. And there we have it, a nice looking square. I usually use a chair or a stool or some masking tape on the floor. Okay, so we are at about the top of the hour. It's almost 4 o'clock Pacific, and then add the number of hours for your time zone. Let's see here. Yeah, so let's go ahead and reconvene at 5 minutes past the hour. Take a break, shake your legs. If you don't have a sorting tray of some sort, I would recommend one because there's all these little tiny parts to have on hand that are going to be in this gray bag. And so we'll be working with those and sensor navigation next. Okay, so we'll see you all at 5 minutes past the hour. Welcome back, everyone. It is now 5 minutes past the hour, and we are resuming our tour through robot navigation. This is a little bit of supplemental material. I just threw these in here, how to do a spiral. You can take a for loop, which we just talked about. So we talked about the for loop. We can take a for loop, and instead of repeating the number of times something occurs, you can actually use that counting value of n in one of the wheel speeds. And you could count upwards to make a wider and wider arc, gradually increasing the wheel speed up to, say, 115, the top speed. The other wheel would start at top speed, and then you just gradually increase the other wheel speed out. Also, in the writing microbit programs, there was a way to count down that's introduced where a third argument, comma, -1 could be added, and you could start at 115 and then end at 0 or 1. And in that case, you would spiral inward. The hourglass, figure 8, or infinity symbol can be approximated by an arc and a straight line and another arc and another straight line. We can also take, say, a water bottle and set it down and then put some masking tape on the floor around it, and then have students tune their maneuver capabilities so that they can get around that water bottle. I like to do this one because later on there's a nice challenge where once you've got contact sensors, you can bump into a water bottle or a spool of something that's heavy enough. They can bump into it with contact sensors, back up, turn in place, do an arc, turn in place again, and then continue going. And that's a really nice way to get a tangible use for the arcs and other maneuvers that they've been tuning. This, I believe, is also supplementary material. It introduces functions. Functions, of course, were introduced in the Learning to Program chapter that we talked about on Monday. And a function is essentially a group of statements with a defined, for DEF, a defined name. And a function can be called by saying, for example, down below, forward. Well, the script, as it had been going through all this, it had made a note of the forward function already. So when it sees forward, it basically jumps to the forward label, and then it does all the statements, and then it comes back. Well, it turns out there's another function immediately following forward, and that one is right. So it goes and it finds the right function, does that job, and then comes back, and then it gets to stop, and it stops. And so this is, the reason this is nice is because these names make it really convenient for the students to get their maneuvers, and then they can just have a list of function calls, and that makes it a lot easier than having everything in line like this. And they can do the wheel speed setting once, and then they give it a name, and then they can think about it in terms of forward, right, and stop. Additional supplementary material. Now, this is not a repeat of the previous diagram, although it looks that way. This is talking about a maneuver function. And with the maneuver function, it actually sets it up so that positive is forward for both servos, because the function can swap the sign from negative to positive of the right wheel. And then a runtime. And this one makes it even nicer to do. And what happens is these are called parameters up here. These are temporary variables that are going to receive values when the function is called. And so when so the script sees the maneuver definition here, and then it sees a maneuver function call on line 12. And that function call passes all three of these values into all three of the, which are called arguments down here, into all three of these parameter temporary variables up here. And then the maneuver executes the maneuver of, in this case, full speed forward for 3 seconds, and then turn in place. Remember that the negative value is now to make one of the wheels go in reverse. That this is, these two positives are for forward, and this is a positive for forward and a negative for reverse, making it turn to the right in place for 0.6 seconds, and then making it stop. So that's an example of little tools that you can additionally give to your students. And then, especially with masking tape, there's all kinds of fun contests that can be created. Okay, next up is circuits. By the way, you can always feel free to jump in with a question or comment as well. So when we do circuits, it's a chapter, and it's fairly short. It starts out with blinking a light that is built into the Cyberbot board. And the statement to blink a light, see how it's labeled P20, and there's a little light right there. So might as well try this one. It's easy to run. Okay, so I'm pasting this into your, oops. Got to try that again. Copy, paste. Okay, there we go. So if we try this one out, it will blink the light. So after this loads, you'll see that the P20 light right there stays on for 2 seconds and off for 1 second. And the idea of how a programmable device, it's got a supply so that it can work. So it has ground or 0 volts. That's the negative terminal of all the batteries in the battery pack. And then the positive supply is 3 volts, and that's established with some parts on the Cyberbot printed circuit board. And that is supplied to the microcontroller that's doing the blinking. And the way it does the blinking is essentially internally, it connects one of its pins that goes to the light in this case to 3 volts, and then it after a sleep statement that makes it stay on for a little bit, it connects internally that same pin to its ground. And what that does is it essentially, previously it gave the pin, oh sorry, the pin's down here. See, my camera's in the way of it. So here's the pin that it's giving 3 volts, and then it's 0 volts over here. 3 volts and 0 volts are 2 different voltages or levels of electrical pressure, and that electrical pressure propels electrons through the circuit. And thankfully, there is a resistor here that resists the flow of current, preventing a surge of current that would burn out the light. And then the LED light is one where when electric current, that's the flow of electrons, passes through it, it gives off light. So that's electrical pressure when, and that's in response to bot 20 write digital of 1. Then bot 20 write digital of 0 is the scenario where P20 is now inside the chip connected to ground, same as the other end of the circuit. So now there's no electrical pressure across the circuit and the light turns off. After that, the next question is, okay, well, how do we build our own circuit? And that starts with understanding how this prototyping area works. There's a 3.3 volt supply, which is what we use most of the time. Seldomly we use 5 volts, and it's especially important that students not connect 5 volts to any of these IO pins. This is ground, so that's the 0 volt negative terminal of the battery pack. And then there's digital to analog. This allows you to set voltage levels anywhere between 0 and 3.3 volts. And this A to D, or analog to digital, are sockets where you can write a script to measure voltages anywhere between 0 and 3.3 volts. And then we build a circuit and write a script, and instead of 20, we're now using 8. And the reason for that is because these little resistors here are connected to P8 and P9. And there's a few things I'd like to show you in the slides about that. The first is just understanding how to connect 2 wires together. The rule for this is that rows of 5 allow you to connect wires and leads to each other. If you're in the same row of 5, like here or here, those 2 wires are electrically connected, and it's because there's a a metal clip, a conductive metal clip that's underneath these sockets. And it's got little jaws that squeeze onto the wires, each wire as you plug it into the breadboard is what these are called. You can also use a wire to connect two rows, and then you'll have more sockets if you need to connect a lot of things together electrically. That's a way to do it. And this is supplementary material again, by the way. So I encourage you to use these slides as you see fit. Here is one where they're close, but they're still not connected because it's not the same row of 5. Likewise, there's a valley here because there's a bunch of clips on this side and a bunch of clips on this side. Each is 5 sockets wide, and there's no electrical continuity between those two. They're not connected until you put a jumper wire between the two of them. And then we saw this just a second ago. So I like to take the students through this one. It's really helpful for understanding, although they do tend to need reminders because they'll build circuits and we'll see that they're in this kind of situation and don't understand why the circuit doesn't work. And and so it helps to help them through that, to say, hey, look at this. You're not in the same row here with those wires, and so that's why the light isn't coming on or the push button isn't being measured, that kind of thing. And it goes on to explain how LED lights work, and I'm going to breeze through most of this. The most important thing for us right now is just understanding that, number one, you have to use the same row of 5, and then secondly, that there's I/O pins here that we'll be connecting to. It's the black sockets to the left of the breadboard. Another common mistake I see is when something's supposed to get plugged into that black P7 socket, a student or even a teacher will instead plug it into the white socket that's by the P7 socket. No, you need to connect it here, and then that's the way the microcontroller and the Cyberbot board can monitor or control the circuit. It won't be able to see it if you plug it in next door. So just so you know, though, there's lots more circuit lessons about how electricity flows through a light, and the resistance slows the electric current down. This is a supplemental one that has just one light. And this is a supplemental simplified diagram that shows how the resistor numbering, or how resistor values, their tendency to resist the flow of electricity, are labeled. And there's a color code, like red is 2. And so we have 2 reds, so that's 2, 2. And then the third bar is the number of zeros to add. That's brown, so we want to add 1 0 because brown is 1. And then the fourth bar is gold, and that corresponds to 5% tolerance, meaning that it's 220 ohms plus or minus 5%. Again, here's another example of the diagram where inside the microcontroller it switches between power and ground to turn the light off in response to bot of pin dot write digital of 1 and bot of pin dot write digital of 0. Then we have push buttons, which we're going to make a version of in just a minute. So you're welcome to peruse this because there's lots more information. Now we have sounds. Sound effects are very popular with students, and there's 2 flavors. There are sound effects, where you can make some funny, spacey sounds. And then there are also musical notes that you can make with the microbit, and those are very popular. And it starts out by plugging a piezo speaker into these sockets. If you have short pins, if you have relatively short pins, basically if you can't feel any resistance when you pull the speaker back off the pins on top, go ahead and insert it from the bottom. And the lesson for this has pictures of what to look out for and how to insert it from underneath instead of above. Okay, so there's that concludes circuits. I realize it was quick, but we need to get to building our whisker circuits. And so the whisker circuit here is one where we'll have little whiskers sticking out in front of the robot. And when it bumps into the box, it'll cause an electrical connection to occur that's been built on the breadboard. And then the script will tell the robot to back up, turn in place, and find a new direction to go. Like so. So yes, this is what it looks like when it's done. And the first thing I'm going to want you to do is gather these parts. I think the best way to view this is actually in the slides. So I'm going to give you the slides, or a link directly to this slide, and then you can fill your screen with it and zoom in and out potentially. I will also give you a link to the page in the lesson, or the lesson page in the chapter. And we'll have you grab these parts. Brown, black, orange, gold is the 10 kilo ohm resistor, and you'll need 2 of those. And then red, red, brown, gold is the code for the 220 ohm resistor. You'll also need 2 3-pin headers and 2 whiskers. So let's go ahead and gather those parts. Use your computer, and I'm going to switch over and just gather the parts myself as well. Okay, so these are the whiskers. There's 1 3-pin header and 2 3-pin headers. And here's a little bag with resistors in it. And I can see a couple of red, red, brown, golds there for the 220. And then the brown, black, oranges look like they're on the other side here. There's 1. And here is the next one. Okay, how am I doing? Looks like that's it. And you'll also need your screwdriver. So go ahead and give me a thumbs up when you're ready. Have those parts gathered. 1 2. 3. You guys are fast. Okay, I only see 3, so we're going to wait a little longer. I discovered a little defect in the Cyberbot I grabbed, it didn't have some parts on the front. It wasn't constructed to spec. Or maybe I modified it and messed it up. So I don't have standoffs on the front. So you won't need to worry about this, most likely because you probably followed the instructions correctly and installed standoffs and washers on the front. I need to correct mine. So here we go. All right. So presumably everybody is through finding their parts. Give me a shout out if that's not the case. Now what you're going to do is take your whiskers and have them sticking out from the front of the board. You don't need to, explode the whole thing like this. Just loosen each of these two front screws a little bit and then hook the whiskers under the screws and retighten them. For best results, hook one above the nylon washer and then hook the other below the nylon washer. And here, I'll give you a link to this slide. Paste. And a link to where the picture is in the chapter. All right, so by the way, turn power off for this. You don't want any damaged circuits, so take out your cable and then set your power switch here to 0 so that both of the power lights turn off. Then loosen the posts up front on the robot and then hook one whisker above the nylon washer. And then you'll want to tighten it so that the whisker is mostly parallel with the breadboard and also pretty tight. So I guess that's visible. You can see that the part of the whisker coming off of the screw is parallel to the breadboard. And then this other whisker, I'm going to hook under the nylon washer on this side. And then also tighten it up so that the part coming, part coming out of the breadboard is parallel to the, and we don't want it, we want it tight enough to return back. Then we're going to have to build the detection circuit on the breadboard, and I will give you a link to that slide. And this one is not yet in the whiskers chapter. It's supplementary material. There is a picture in the whiskers chapter that's usable, but I really think this one is quite good. If you prefer this one, that's fine too. It's the slide immediately afterwards. So either of those will allow you to build the whisker circuits, just so you'll want to make sure that there's an air gap, and you'll want to make sure that the 3-pin headers are inserted all the way into the breadboard, and that there's a gap between the whisker and the 3-pin header, and count the number of rows down. So 1, 2, 3, 4, 5, 6. You're going to have a 3-pin header in the 7th row, 8, 9, and the 10th row. I'll leave that up and just build it from there, as opposed to, well, maybe I better, since you've got this in front of you, hopefully, and give me a shout out if those links aren't working, because then I'll switch back to having it on the Zoom. Okay, so we are putting the 0 or 1, 2, 3, 4, 5, 6, 7. See how nicely the whisker bumps into the 3-pin header when I press it? That's what we're looking for. And then 8, 9, 10. Now the other whisker. Looks good. Interestingly, I feel like I'm off by 1. That works, but I feel like it's better nope. Going back to the exact way it is on the schematic or on the wiring diagram. There we go. All right, then P9 and P7 are the red, red, brown resistors, and they go from there to the same row as the 3-pin headers. So grabbing my 2 red, red, brown resistors, connecting them into the same row as the 3-pin headers. And then the other end of the lower of the 2 goes to P7. Looks like I missed and got it in P6. Be careful about that. And then the next one goes into P9, like so. Then the brown, black, orange resistors also have to go in the same row as as everything else. And then they get jumpered up to 3.3 volts. And a word of caution, make sure that the resistor leads are not touching each other. So hopefully it's visible here that I have an air gap between these 2 resistors. This resistor is not touching the 3-pin header post, and there's air gaps all around. Oh, I guess it's not really visible. There. Now you can see that that the resistors are not touching each other or the other posts. So this resistor's lead and this resistor's lead, and these posts are electrically connected, and then this resistor's lead and this resistor's lead is connected to this post electrically. And then they're not connected to each other by accidental contact between leads. So go ahead and give me a thumbs up when you've got this built. Oh, and I should say one other thing. Again, be careful to make sure that your resistors on this end are plugging into the black sockets, the black socket next to P7 and the black socket next to P9, not the white sockets on the breadboard. Those should be clear. And then likewise, up above here, see where it says 3.3V? That's the label for these black sockets. So these 10K brown, black, orange resistors need to plug into these black sockets immediately below 3.3V. Ari, did I miss any thumbs up? Got one thumb up, good. 2, all right, good job, people. 3, oh, excellent. 4. Fantastic. So let's get you the test code to test and make sure the whiskers work. In your chat is going to be the test code. Oh, well, gee. When I hit send to microbit, there was a little problem because there's no microbits appearing in the list. And the reason why is because I forgot to plug the programming cable back in after dutifully disconnecting power. So once you're done with your whisker circuit, plug your programming cable in. And you can set your power to 1. And then hit send to microbit, select it in the list, hit connect. Now, once the code is flashed, what you can do is press the right whisker up against it's going to be the left post, but up against its post. And you should see a light on the right side of the microbit, closer to the A button, light up when you press the right whisker. When you let go of the right whisker, when there's an air gap between the whisker and the post, then the light should stay off. And actually, when no whiskers are pressed, no light should be on. When the left whisker is pressed, the A light on the left side of the microbit should light up. It's very important that that all three conditions work. And actually, there are 4 conditions. There's 4 different ways that things can go here. First one is no whiskers are pressed against their posts, so no lights are on. Then right whisker pressed, right light on, left whisker pressed, left light on, and then, of course, both whiskers pressed, both lights on. So make sure that it passes all 4 tests, and I have to really emphasize this with the students because invariably there will be 1 or 2 who skip the test, and then their robot just kind of keeps on doggedly pushing on a surface as opposed to backing up after detecting it and finding a new direction to go. Let's see here. What if both lights are lit? Should the whiskers be touching at the start? The answer is no. The whiskers should be not be touching at the start unless you're pushing them into the posts. If you're pushing them into the post, then yes, both lights should be on. But the way the whiskers should be positioned is so that there's an air gap between each whisker and its post. So the post that the whisker will bump into when you press the whisker, sorry, let's try that again. So there should be an air gap for the right whisker over here. It makes its contact on the left side, and right where my screwdriver blade is, there should be an air gap when the whisker is at rest or inactive. When the contact is detected, and by the way, whisker switches are essentially what's inside a industrial contact switch. So then when you press the whisker against the 3-pin header, then the light should be on, and then you let go of it and the light will go back off. So the whiskers should not be touching the posts. They can be touching each other, that's fine, but they cannot be touching the posts. Okay. Only getting double light when not touching posts. Me too. Double lights when not touching posts. What would be causing that? I wonder if the pull-up resistors are incorrectly connected. Yeah, look at that. So, so if you have double lights when not touching posts, something is unplugged. And so the thing to do is to check and make sure that each lead, see, when I unplug anything, when I leave, essentially, yeah, when I leave it all unplugged, if there's anything incorrectly plugged in, if it's not plugged into the black P7 socket and the black P9 socket. So one really common thing is that you're off by one, and it's important to look straight, look at the IO pins from straight above to make sure that you've got your 220 ohm resistors in the P7 socket and the P9 socket. Then you need to make sure that they're in the same row as the posts, and that the 10K resistor is also in the same row as those posts, and that it's coming up and plugged all the way into a 3.3 V socket up top here. And again, those are black sockets that are outside the breadboard. And so as soon as you've got all your connections correct, then you should see no lights on when the whiskers are not touching the posts, and then the lights only come on when the whiskers are touching the posts. Circuits can tend to be somewhat unforgiving if a mistake is made. If only one mistake is made, the whole system doesn't work the way you want it to. And so until all errors are corrected, it's important to continually go back to this test until it passes. And it's a really good exercise for students to learn attention to detail as well as the basics of circuit building. So what I am going to do is paste in some navigation code for you. So for those of you who have got your robot to pass the test, it's ready for this navigation code. For anybody whose robot has not passed the test, make sure to get your circuit errors corrected first. And we can also help you after the class just to get it troubleshot. But this is, I just pasted in the high speed version or the medium speed version of the script that will navigate and turn according to the whiskers. But if I remember correctly, I'm not exactly happy with the way it performs. Let me just quickly test that. I might adjust some of the numbers and then repaste it in. Let's see how it behaves. Okay, this is going to go kind of fast here in the limited space I have. Well, it's actually turning a little farther than I want it to turn. I thought it would not turn far enough. Let's see here. So I think my turn in place times for backwards is fine, but I might go to 600 or even 500 for the turns. Let's try that. For the amount of time a turn takes. That's very interesting. Gonna have to cut it down to 400. Well, that's about a 90-degree turn at 400 milliseconds. Well, maybe a little less. Yeah, it's just under 90 degrees, maybe 70 degrees right now with a sleep of 400. I'll paste that one to you. Or actually, since all I did was change these 800s to 400s, you can do that too. Okay, let's see. What do we have as far as comments? All right, well, what I'm going to do is just finish the presentation, and then I'll help anybody who wants to troubleshoot their whisker circuits after the after we've stopped recording. Make sure both whiskers work here. Yep. So that's essentially the behavior we're looking for. And then as far as a wrap up of the day goes, and again, we'll go ahead and talk more about it. What I do is I explain to students that the whiskers, there's a lot of supplementary material on how the whiskers actually work and what conditions occur when they're pressed or not pressed in terms of voltage. And then that's discussed in terms of schematic too. Again, this is all supplementary material. In the book, it basically says, well, if it's not pressed, it's 3 volts. And then that results in bot 7.read digital returning a 1. If it is pressed, the IO pin will sense 0 volts coming from the whisker circuit, and then bot 9 of read digital in this case would return a 0. But again, there's a lot of slides to break it down into whatever level of detail you need for your students. And this is also supplementary material where you can talk about, ask the students some questions about the whiskers, that if it returned a 0 here, what would get executed? Well, if whisker right equals 0, which it does in this scenario, this statement would evaluate to true, and so it'll make that light up. And let's see. And then there's the same idea, the same kind of diagram for monitoring a circuit and how the microcontroller can detect 3 volts or 0 volts and then return a 1 or a 0 depending on what voltage the whisker supplied. So this is the exact opposite of no, not the exact opposite, actually. It's very different from shorting to ground to turn a light off, or shorting to 3 volts, 3.3 volts to turn a light on. This is not affecting the circuit in any way at all. What it's doing is it's silently monitoring whatever the circuit does. And in this case, when the whisker is not pressed, the circuit supplies the IO pin with 3 volts. And when it is pressed, it supplies it with 0 volts. And then the script will get a 1 out of that or a 0 out of that, and it'll use it in its decision-making process. So for Friday, what we're going to have you do is go through and build and test your infrared circuits. And we'll probably continue testing them on Friday. In fact, I'm kind of leaning towards just having you try to carefully build it, and then we'll do the testing on Friday. So we'll skip the testing infrared object detectors. We'll just build the circuit. And these slides here talk about essentially how an infrared light is one that humans can't see, but silicon can see very well, or at least the kind of silicon that's designed to sense light. And so these are the parts you'll be gathering. There are 2 different shapes. The taller dome shape is the infrared light emitting diode. And then there's a shorter dome shape that's a phototransistor. It has a flatter top, so that you'll be looking for a relatively tall dome shape light. That's your infrared LED. And you'll be putting it into a little protective container that prevents it from shining light anywhere but forward. And so you'll be putting the pins through, and there's 2 holes in the bottom of this infrared LED standoff, and 1 pin should go through each hole. They can't be squished together and go through the same hole because they'll be shorted together that way. So anyway, put the LED in and then snap the cap on. There's a little cap that snaps on, and your assemblies will look like this one when they're done. You'll need 2 of those. And then this will be the circuit you build. Again, you'll need to be really careful with all your BOM sites when you plug the resistors in, and also careful of the color codes of the resistors. Again, don't test it or turn power on. We'll talk about that on Friday. Just skip testing, just get it built to the best of your ability, and that'll be great. And then one other item for Friday will be that you might receive an email that looks like this, basically saying, hey, we've added you, given you membership to learn.parallax.com as an educator, so please go and sign in and update your password. Or it might look like this. Now, if you've already gone to learn.parallax.com, you can go to learn.parallax.com to log in by just going to learn.parallax.com, then clicking educators, and then selecting login. And I'll send you an email about this. If you don't remember your password, you can just click the lost password link. If you've had if you signed up for Parallax a while back at learn.parallax.com and don't remember your password, you can get it back just by supplying your email. And that's it for today. Remember to unplug power from the bot when you are done. I know some of you are going to stay on for a little bit to get your Whiskers circuits troubleshot and to get that navigation with Whiskers application up and running. So that's fine, but when you're done with that, unplug power for everybody else who is done for the day and ready to take a break. The important thing is going to be to there we go. It's to unplug power right there. That way the batteries can't drain by supplying the microbit with power while it continues to run its script or anything like that. Actually, it doesn't pull much power, but if it sits for a long time, you could still drain your batteries, and then you would also unplug your USB cable. So unplug power when you're done. Again, I will email you that homework assignment. Just kind of gave a quick overview of it. So that is it for today. Thanks for coming, everyone, and we'll look forward to seeing you again on Friday. And again, after this, we'll go ahead and work with anybody who's still troubleshooting their Whiskers circuit. Thanks again, or thanks for coming. We'll see you on Friday.